Okay, so let's get started. For people on Zoom, you guys can hear me, right? Can I get a signal? For everyone joining on Zoom. Okay, perfect. Okay, so let's get started. So this is the second lecture of your database course. So let's just recap a little bit what we have been talking about on Wednesday, right? So in last lecture, we actually take multiple examples and try to think about essentially how to close this, in my opinion, very fundamental gap. That is, you have a whole bunch of information and knowledge you have about this universe. On the other hand, you want to extract insight from your data. Because your data is not that useful if you cannot get insight out of it. So on one hand, right, the way we are going to think about information and knowledge in this course is by thinking about that as a collection of facts. So they are the things that you know that hold true in this universe. And then you can actually query this collection of facts. There are different ways that we can query it. So you can have some logical formula to say, yeah, this is how I want to do logical reasoning. Given this collection of facts, generate a whole bunch of facts that I know going to hold, right? This is one way for you to actually get information or insight out of this collection of facts. And there are other things you could do, right? For example, you could manipulate this. Manipulate might have a negative tone to it, but enrich this collection of facts, right? We will know new things about this universe. You can add them to this collection of facts to enrich it, and then can continue to query this new collection of facts, so on and so forth. And of course, there are other ways that you can extract insight from this collection of facts. For example, you can do statistical analysis, you can do machine learning, which we are not going to talk about in this course. But there are so many different ways you can extract insight from your data. And in this course, we are going to focus on how to do that via logical reasoning. And we also talk about, set some expectation about what we are going to cover in this course. Right? Given this the thing that we want to do, right? So of course, we need to understand how to represent and how to organize. Yeah, for everyone joining on Zoom, can you mute yourself? Okay, great. Yeah. Now the audio is connected to the room and connected to Zoom. It's very fancy, but the problem is whenever someone speaks on Zoom, you guys hear it. Yeah. Okay. So the first question is actually how to represent and organize this collection of facts, right? So we are talking about things like a data model, right? How do we think about these facts? And also how to design, as you will see, a better organization of the data. Sorry. Yeah, something that we call database design theory that we are going to learn toward Easter. And then how to design a query language to represent the thing that you want to query. Right? And we are going to talk about that. And we are going to talk about giving a data model, giving a query language, right? How to actually run those queries as efficient as possible. And we are talking about how to actually query like terabytes of facts, how to have thousands of concurrent queries running over a single database. So these four components are what we are going to explore together in the next 3 months. And today, let's look a little bit deeper into data model and into query language. So the thing we are going to focus on, actually not only this lecture, but also for the whole semester, is something called relational model. The whole thing started half a century ago, and today is a dominant kind of type of database system that you are going to see in practice. So the one of the most popular today is the focus of the course. And by using a relational database, right? So we also talk about multiple properties that we want from a database system. We want to have data independence, that the program you are writing, the query you are writing, shouldn't rely too much on how your data are organized, how your data are stored on your hard drive. We want to have declarative, efficient data access to make sure when you are writing a query, as a user, you do not worry too much about how to optimize the performance or the speed. We want to have transactional access. We want to have kind of a generic abstraction such that even if you have thousands of queries that you could potentially ask, you are all writing them in the same abstraction. So that is our goal. So in this lecture, we are going to talk about what is relational model, how to model your data with relational model, and we are going to talk about two different ways that you can query your data that is stored in relational model. So the first way we are going to talk about is something called relational algebra. It's actually try to represent your query as set operations. So as you will see, this is an imperative way for you to query your data. Imperative means like in the sense that you are actually telling the machine how to get the answer for you. So second thing we are going to talk about, probably need to wait until next Wednesday to go into that, is something called relational calculus. This is actually very different from relational algebra. It's actually a lot of fun to put them side by side and try to compare them. In relational calculus, it's declarative, in the sense that you are not going to tell the machine how to get the answer for you. Instead, you are going to specify the condition of the result that you want. And the way for you to do that is to write down your query as a logic formula. And then that actually tells the system, okay, as long as the data satisfies this formula, I want you to return that. So these are two very, very different ways for you to query data that is stored in relational model. And to some extent, as we will see in the next lecture, there's also some kind of equivalency between the type of query that you can represent in these two very different query languages. So hopefully after, So hopefully after next lecture, you are going to understand what is relational model, how to query them in these two different query languages, and what is the difference and relationship between these two different ways to query data. Okay, so now let's start. Let's talk about relational model. So to really understand what is data model, right, it essentially try to make a statement about, in your mind, what is really the data. But no matter what you think about it, right, so data is not really a sequence of 0 or 1s, right? I mean, that doesn't really have too much value if you think about data as a sequence of bits, right? So what's interesting about data and why we are so excited about it, it is the knowledge we have about our world. And when we talk about the data model, essentially we are asking a question, how can we represent this collection of knowledge? Or how can we inference new knowledge from the old ones? If you have different answers to these two different questions, it will give you different type of data management system. And the thing we are going to focus on in this course is, again, by thinking about knowledge and data as a collection of facts, and by thinking about the ways of doing inference as a mathematical logical formula. And this gives you the relational model. So in relational model, the knowledge that we want to represent is actually pretty old. People have been doing that for thousands of years. Is we want to say, okay, in this database, the way I think about knowledge is something that looks like this. Is something you can put into a table. Well, we have been doing this for thousands of years as human, right? So this is actually something we want to start with. Now let's think about how to model this, right? So how to model this type of knowledge. So to define a relational model, there are actually two different components in the relational model. The first thing is something that we call schema, which actually tell you what is your data looks like. It has nothing to do with the content of your database, but more like, so what is the shape of my data? What is the type of my data? And that is something we call schema. So let's look at this very ancient database and try to think about if you were to kind of design the schema of this, right? So what are the information you need to encode? Well, the whole thing is a table, right? So hopefully this table has a name, right? And also if you look at the structure of this table, so there's a whole bunch of kind of columns, right? And if you're familiar with tables, right? So the property of this column is that if you take any single value in the same column, hopefully they will have the same type, right? You could have a table contains all the information of students, right? Every single row of the table is a single student. You take one column, for example, the name of the student. No matter which row you take, as long as you are taking value from the same column, right? Yeah, highly likely you are getting, if the table is correct, you are getting values of the same type, right? So this is the attributes, the columns, a whole bunch of columns. And then if you look at each row, right? So it's actually one instance of relationships between entities, right? Think about, again, like the table containing information of students, right? Every single row corresponding to a single student. Student have ID, has name, right? So if you take that row, it gives you the relationships between this student and that student's name, right? This is pretty much what we have in a table, right? The whole thing contains a collection of tuples or relationship between entities, right? And for every single entity, right, and if you take every single column, right, you have essentially some attribute of certain entity. So that's a table. Now let's try to define this in a more formal way. Okay? In relational model, when we define schema, this is what we mean. We have the schema for your database, which contains a set of relations. And each relation looks like a table. Okay? So the schema of database contains a set of schemas for relations. For each relation, right, so we can also define the relation schema. It has a name to make sure you can talk about that relation. It contains a set of attributes or fields or columns, right? So no matter what however you want to talk about it, it has a set of columns, attributes. And for each of those attributes, you have the name of the attribute, and you have the domain, which is, so you can think about it as a type of the information you can put into that attribute. For example, integer or string, right? So this is pretty much it. This is the schema of a relational database. So let's just look at one example, right? So this is the schema of one example relation called students, right? Here is all color-coded. You can actually read that correspondingly, right? So here the name of this relation is students, okay? And then it contains a set of attributes. You have student ID, you have name, you have login, age, GPA, right? So this is 5 different attributes. You can think about that as 5 different columns in the same table. And for each attribute, you also have the domain, like the data type, right? For example, the name of the student is a string, right? So this is how you represent the schema of the student's relation. Okay? If you think about this as tables, right? Pretty much this schema, a schema is used to describe what your data looks like, right? So if you give me this schema, you are essentially saying to the database that, okay, so my data can be organized into a table that looks like this. The name is students, it looks like a table, it has 5 different columns in that table. The first column is called student ID, the second column is name, right? Whatever information you put in the second column, the name, it's better to be a string. That's the data type. So this is the schema, right? As you can see, once we define the schema, right, the system or you have some idea about what data actually looks like. So there are multiple things we need to be careful. The first one, when we talk about schema, it actually doesn't contain the content if you think about that as a table. Okay? It only tell you, okay, this is the shape of my table, this is the name of different columns. It doesn't contain the content. It's only the header if you think about relation as a table. So now let's think about the content. Okay, now we have the schema. Let's fill in the content. So we call the content an instance of this relation. Okay, so here's how we define it. So assuming I give you a relation R with the following schema, that the name is R, it has n different attributes, f1 to fn, and every single one of them have a domain, a data type, d1 to dn. Assuming that's my schema. Okay, it defines a table with n columns. Right? So we say, now let's try to model the content of that relation. Right? An instance of this relation, we call IR, right? is simply a set of tuples that satisfy the data type constraint. Okay? An instance is simply a subset of this cross product. Okay? It's simply say, yeah, I mean, if I think a relation as a table, an instance of this relation, yeah, is the kind of the table's content. Not all the ways you can fill in the value to a table is consistent with my schema. For example, if I say the first column is integer, you cannot put a string there, right? So this essentially says that, okay, an instance IR of a relation R is simply a collection of tuples that respect my data type constraint. Okay? So intuitively, right, if you think about instance to be the content of relation, if you think about relation as a table, so as we will see, there's some small difference between relation and a table, right? So, but if you think about it as a table, this is what it is. It's the content. Now let's look at one example, right? So assuming you have a relation with the following schema, the students relation, this is one instance of that relation. As you can see here, we have 3 students, right? The first student have ID equals 0, name equals A, login equals D, so on and so forth, right? You just fill in the content. So there are certain things we need to be a little bit careful about. And that actually goes into the difference between a relation and the table you see on a piece of paper. The first thing is that in the definition, right, the instance is a set of tuples, not a list of tuples. It means that it means 2 things. The first one is in our current definition of the relational model, we are assuming there is no duplicated tuples in a relation instance because it's a set. I cannot have 2 elements that's the same in the set, right? That's different from a table on a piece of paper, right? So it's a set of tuples. So there's no duplicates. And second, because it's a set, the order doesn't really matter at all. The system have no idea the order of the data being stored because simply it's a set. There's no order. Okay? So this is something really important about relational model. So later, after a couple of weeks, when we play with a real-world database system, you will see in real world, in practice, it's kind of a little bit more complex compared with this definition of relational model that we have. Right? In real-world database, a relation is actually a bag of tuples. It's a multi-site, right? So you can have duplicates. But again, for a real database, there's also no order between those tuples. But in this course, when I talk about relational model, we always take this simple definition because it doesn't really make sense to make that too complex. We think about relation as a site when we talk relational model. We think about relation as a bag of tuples, a multi-site, when we actually play with a real database. Okay? So this is an instance of relation. And there are more things you can define in a relational model. So we can introduce a notion of key. Okay? So let's say we have a relation R with some schema, right? And then we say, yeah, so we can define something called candidate key, which is a set of attributes. This is the type of candidate key. Okay? So candidate key is a minimal set of fields or attributes that identify each tuple uniquely. For example, you have a student table, student relation. One candidate key could be the ID of the student, which means that, yeah, if you give me a student, if you tell me the ID, right, I can uniquely identify a student. That is, you do not have 2 students share the same ID in this instance. Okay? So, and then we can pick one candidate key and set it as primary key. Okay? When we define the schema, and we can say, yeah, we just mark a subset of attributes by underlining it to say, this is my primary key. Okay? So, which means that in this relation that I want to model, if you gave me a unique value of all the attributes in the primary key, I can uniquely identify a tuple in any relation instance. So in relational model, we assume every relation must have a key. When you define the schema, you always need to underline the primary key. And that's always possible, okay? Why? Because relation is a set. In the worst case, the whole set of attributes is your key, right? You always are able to identify a key in relational model. But often in practice, right, so it's a much smaller subset. So now let's look at one example, and it will become clear what we are talking about. So this is the student relation, right? As you can see, we say, yeah, in this relation, my primary key is the first attribute, okay? The student ID. What does that mean? It means that in this database, when I model my data, my model of the student's relation has a following property. That is, if I know the value of the primary key, that is, if I know the value of student ID, I can always uniquely identify a single row in this table, in this relation. So essentially, try to define what is a valid instance for this relation, or what is not a valid instance for this relation. That is what we want to achieve via primary key, or candidate key. Right? So this is a valid instance. That is, okay, I have 3 students, and if I say, okay, the student ID equals 0, it's always identified to the first row, right? If I say the student ID is 1, it's always identified the second row. This is a valid instance, given this schema. What is not a valid instance? This is not a valid instance. If you think about why, right, is in this instance, it actually violates your primary key constraint. Why? Because if you look at the first 2 tuples in this relation, yeah, so there are different tuples, but they share the value of student ID. They're all equal to 0, which means that even if I know student ID is 0, I cannot uniquely identify one tuple in this instance. Okay? So this violates my key constraint, my primary key constraint. So essentially, the reason we want to introduce this notion of key is try to say, yeah, some of the instances are valid, some of the instances are not valid, right? So I try to draw the line about what you can actually put into that relation as instance. So yeah, so this is like intuitively, right? When a subset of attributes is a key, it means that, right, in whatever valid instance you put in the relation, right, you cannot have 2 tuples sharing the same value on the key, right? For the student case, essentially says that every single student I put in the table need to have a unique ID, right? So that is why we have that definition. So we can go a little bit more formal to actually define what this is. So essentially, if you gave me a relation with the following schema, the name is R, has 3 collection of attributes. You have K, you have A, you have B, right? Have their own data type, dk, da, db. And then the primary key is K, okay? This set of attributes. Essentially, what it says that is whatever instance of the relation is, it must satisfy the following condition. That is, it needs to contain a set of tuples that satisfy the data type constraint. Okay? So it must be a set of tuples belongs to dk, da, db, the cross product. It must be a tuple of that type. But that's not enough. I have some additional requirement. That is, if you give me arbitrary 2 tuples, KAB, K prime, A prime, B prime, if the key actually matches each other, if K equals to K prime, I must be able to imply that the rest of the attributes will take the same value. Okay? Formally, this is what it is. Intuitively, it means that what is a valid instance? It means that if you give me an instance, I cannot find 2 tuples that are different but sharing the value on the key. Okay? Make sense? Yeah. this is another thing you can define in the relational model. So this is just one way for you to actually constrain the set of valid instances. So as we will see later in this course, there will be a whole bunch of different ways for you to say, yeah, this is a valid instance, that's not a valid instance. Okay? But this is just a simple way for you to define that. Okay, this is pretty much about relational model. There's schema, there's instance, there's the key constraint. Okay? Now let's look at some example and try to think about how can we use this to model, some data that you might have. For example, we want to have a database that contains information about university. Okay, what do you have in a university? You have professors. Each professor has a personnel number, has a name, has level, has office, for example. That could be the data you want to model. You have students. You have lectures, right? And then some lectures are prerequisite to other lectures. There's the relationship between lectures, right? And students attend lectures. So assuming this is the data that you have that you want to model inside your database. So how to store all the information in a relational model, right? How to design the schema, and also what are the valid instances of that schema. So now let's think about this. Let's think about how to store the information for professors, okay? So what is a schema? Yeah, so we could define a relation with the name professor, right? Contain all the professor information. The schema could be, for example, I could have the attribute personnel number with the type integer, right? To actually store the personnel number of professor. I could have the name of the professor, the level of the professor, the office of the professor, right? So if you model your data in this way, you are going to have a relation that look like this. You can actually write it down as a schema like this. It's a professor with 4 different attributes and have their own corresponding data type. So what is the instance of this relation, right? Oh, again, the primary key is the personnel number of the professor. So what is the instance of this relation, right? So yeah, it's a set of tuples. It's a tuple with 4 elements consistent with the data type that you have in the schema, right? So this is one example instance that you could have for this relation, right? Has 3 different professors with different personnel number, right? With a name, level, and room, right? This is a valid instance. Why do we say it's valid? Yeah, because it's also satisfied 2 different constraints. It satisfies the data type constraint, right? And also it satisfies the primary key constraint. That is, if you take any 2 tuples here, right, none of them will share the same personnel number, right? Every single professor have a unique personnel number. And this is just another example that's actually not a valid instance of this relation, right? Why? In this case, it's actually violate the primary key constraint. That is, yeah, these 2 professors share the same personnel ID, which is not what I want because I told you in the schema, my primary key is personnel number. And we can do this exercise for essentially other type of data, right? So how can we model the data for students? Right? We could have relations say, yeah, this relation stores information about students. The schema could be we have personnel number, which is our primary key. We have the name, we have the current semester of the student, for example, right? And then you have a schema that looks like this. So what is the instance of this relation, right? I mean, it's a set of tuples, right? Set of actually triples, right? So it only have 3 elements. And then you have, this is one example, valid instance of this relation. Satisfy the key constraint, it satisfies the data type constraint. And this is another example that's not a valid instance because it violates the key constraint. This one actually not valid key constraint. Yeah, so this violates the constraint that relation are sites because as you can see, these are the 2 examples that look exactly the same. Okay, so relation is a site, instance is a set. Okay, you cannot have an instance have duplicate tuples in relational model. Okay, so this is why this one is not a valid instance. It doesn't violate the key constraint because these 2 are the same tuple. Okay, it violates the constraint that the relation need to be site. Okay? And you can have other relations. For example, here's a whole bunch of lectures. We could have a relation called lecture, contains information about lectures. Each lecture has an ID, which is the primary key, the title of the lecture, the credit point, right? Which professor is teaching this lecture, right? And then you have a schema that looks like this. What is the instance of this relation, right? Yeah, so it's a tuple of 4 different elements. And this is one example instance of this relation, right? Has a whole bunch of lectures, right? This is a valid instance. You check whether it's a set, whether it satisfies the data type constraint, whether it satisfies the key constraint. Okay? And this is actually also a valid instance, right? So in this case, right? So this is actually a very weird instance if you look at this, right? So it simply means that in this universe that we want to model, there are 2 database courses with different lecture ID. Yeah, and you can put the weirs into the instance, but it's valid given your schema. Okay? Yeah, it satisfies the data type constraint. It's a set. It also satisfies the key constraint, right? So simply, yeah, it's kind of, yeah, the lecture ID is unique. So it means that, right? So even when you define a relational schema, it actually gives you some way to say this is a valid instance or not a valid instance. But even that, you could put some weird things into that instance to make that still valid. Okay? It's your job as a user, right, to make sure the thing you put there actually makes sense. Right? Database can help you to do some of the checking, right, to make sure it's not obviously wrong, right? But as a user, right, the thing that you actually put in actually also matters. And then we have other informations. For example, there's the prerequisite relationship between different lectures, right? Before you take some lecture, you need to take some other lecture, for example, right? In this case, how can you represent that information? And you could have one relation called requires, and then you put the prerequisite as one of the attributes, and you put the follow-up lecture as another attribute. So one thing that's interesting about this is, let's think about this, that you have this require relation. What is the primary key in this example? Should I put the prerequisite as a key? Should I put the follow-up as a key? Should I put the combination of them as a key? Yeah, that's something actually not that trivial. So let's think about that. There are multiple options, and then let's think about what is the implication of each of the options. The first option is to put prerequisite as the primary key in the schema. What does this mean, right? And second option is to put the follow-up as the primary key. The third option is to put the combination of them as a primary key. There's no fourth option because you always need to have a key. Yeah. So let's think about this instance and to think about whether this is a valid instance for each of these 3 different options. Okay? So I have only 2 tuples in this instance. Essentially, the lecture 5001 is a prerequisite of these 2 different lectures. So under option 1, right, it's not a valid instance. Why? Because if I set prerequisite as a key, I cannot have 2 tuples sharing the same prerequisite value, right? In this case, clearly, it's not a valid instance for option 1. For option 2 or option 3, it's fine, okay? Now let's look at this example. Now we have 2 different courses are the prerequisite of the same course, okay? 5041, if you want to take that course, you need to take that 2 different courses. Is this a valid instance under the 3 options, right? Yeah, if you look at the first option, it's actually valid, because if I set the key constraint as prerequisite, it's fine, right? These 2 tuples have different value of the prerequisite. It's fine. But the second option is not valid anymore, right? If I have this instance, it's not a valid instance if your primary key is the follow-up course, because I have 2 tuples in this instance share the same value of the follow-up attribute. And for option number 3, it's valid, right? So if you look at this, it actually tells you a little bit about how to pick one of these 3 different options. There's no right option, there's no wrong option. The thing that matters is whether each of these really describe that universe that you want to model. If you live in a universe that there's always kind of one-to-one linear relationship between the 2 different courses, right? So one course can be the prerequisite, can be the prerequisite of only one other course, right? So if you have that, some of this option will be better or will be correct. Okay? If you live in a different universe that, yeah, it's actually not that strict, one course can be the prerequisite of multiple courses, and one course can require the prerequisite, like other courses, whole bunch of them as prerequisite. If you live in that type of universe, if that is what you want to model, then option 3 is probably the thing that you want to have. So again, when you design the primary key, right, so there's no right answer. There's no universally correct answer to what is the right key. The thing that you need to do is to look at your data, look at your application, and think about essentially what makes sense. And then you can make the decision about which subset of attributes that you can have as a key. So among these 3 different options, right, so option 3 seems to be kind of a natural choice, right? So essentially, one course can be prerequisite of multiple of them, and one course can require multiple prerequisites, right? So it seems to be something that kind of makes sense in many universities, right? So if that is the case for you, right, you could have the schema look like this. That is, you have a requires like relation, 2 attributes, and the combination of them, right, is the primary key. So let's look at some other information, right? For example, student attend lecture, right? If you want to store or model that piece of information, what should you do? You could have a relation called attend. With the following schema, you have the personnel number for the student as the first attribute, and you have the lecture ID as the second attribute. Both of them will have type like integer if you store both of the information integer in other table, right? Again, what is the key, right, in this case? Yeah. So what are the options, right? Yeah, you could have the student number as the primary key. You could have the lecture ID as a primary key. You could have the combination of them as primary key. Yeah, again, there's no right answer about, no universally right answer about what is a good option. It all depends on whether each of these options models the thing that you want to model. For example, if I have this instance, right, there's 2 different students taking the same lecture, right? So it is valid under option 1. It's not valid under option 2 if your lecture ID is a key, right? Clearly, you probably want multiple students in the same lecture, right? And if you want to model that type of universe, you cannot do option 2 because that's going to reject this type of instance. So again, for this type of instance, right, one student's taking multiple lectures, right? If you look at the 3 different options, right, it's option 1, and this is not a valid instance for option 1, right? Because valid the key constraint if you have a personal number as a key. Right? If in your university, right, one student can only take 1 lecture, right? And then this is fun. Go for option 1 is fun, right? But if you want to model a universe that one student can take multiple lectures, then clearly you cannot really do option 1. Okay? So again, option 3 seems to be a more natural choice. One student can take multiple lectures, and fortunately, there are multiple students in the same lecture, right? So, and then if that is the thing you want to model, go for option 3. Have a relation with the name attends, have 2 attributes, and have their combination, okay, as the primary key. Okay, so another piece of information is students need to take tests, right, in lectures and get a grade, right? In this case, I think we can all be pretty familiar with this exercise now, right? With a relation called test, personnel number of the students, lecture ID, the grade, right, the student get in the test, right? What is the key, right? So in this case, right? So you set the combination of the personnel number and lecture ID as a key, right? So, and this actually likes fun, right? So this is a pretty natural thing to do, right? So essentially that means that for every single student, for every single lecture, there's only one grade. You cannot have like one student, one lecture, have two different grades, right? And if you live in a world that can happen, then put the whole thing as a key, okay? Yeah. So, yeah, this is pretty much one example about how to use relational model to describe your data. And also what is the implication of multiple design decisions that you could make when making such a design, okay? So let's just try to recap, right? If you want to model that piece of data, one possible design of the schema could look like this. Have professor relation, student relation, lecture, right? Requires, attends, test, right? This is your database schema. Contains a collection, a set of relation schema, okay? And then you have your choice of your primary key. And then this is one possible instance of this database that contains a set of relation instances. Each one of them contains a collection of tuples that satisfy the data type constraint and also satisfy the primary key constraint. Yeah, there's something that we need to be a little bit careful about relational model. So first thing is there are multiple ways that you can design a schema. Okay, we just look at them and we can pick different primary key, right? So there is something that can be more complex, right? You can, for example, you can put the professor information and lecture information in the same relation. There's nothing stop you from doing that, right? There are multiple ways to design a schema to describe the same piece of data, okay? And different designs might have different consequences, different implications, and different pros and cons. So we will see how to actually design a good, we will see how to define what is a good design later in the course around kind of before Easter, I think. And also we will think about how to design good schema. After we define what is good, we are going to look at how to design a good schema later in the course. Okay, so this is the first half of today's lecture that we actually try to define relational model and give some example about how to model data in a relational way. So now let's take a break. When we get back, we talk about how to query the data in a relational model by using what we call relational algebra. Yeah, let's get back in like 9:15. Yeah. So if you have any questions, you can just, come front, ask me. And if anyone have questions on Zoom, I'll be here to answer them. Just speak up. Okay. Okay. Great. So in the first half of the lecture, we talk about relational model, right? You have your application of data you want to model, right? Here's how we fit them into a whole bunch of relations, right? It's very simple, right? So that's the beauty of modern relational database system, that the data model is actually very, very simple. You can pretty much fit everything that you want into a whole bunch of relations. But that's not the end of it, right? So now we have your data. Now we know what the data really is inside your system. Now let's try to get information out of it. And the way we are going to do it is by writing what we call some queries, and in different query languages. So the first query language that we are going to talk about is also very simple. It's something called relational algebra. Yeah. Okay. So what is a query? What is a query language? So query is a function that takes as input your database instance. Again, instance is the content of those relations, right? Given any instance, the goal of the query in the relational model sense is a function that takes as input this database instance and output a new relation instance. You can think about the query as a function that takes as input a whole bunch of tables and output a new table, okay? So all the functions that satisfy this input and output type, in principle, is a query. It might not be a query you are able to write down, right? It might not be a query that you can run efficiently. But in terms of what it is a query. Take as input a database instance, give you a new table, okay? So a query language. Okay, so, sorry. Sorry, I was muted on Zoom. Okay, yeah. So, okay, so now you guys can hear me, right? On Zoom. Okay, perfect. Yeah. So, yeah, you can find what is missing on the recording. Yeah. So it's recorded. So, okay, sorry. We were talking about what query language is. Yeah. So query is something that takes as input a database instance and output a table. Okay, that's what it is. And the query language are the machine understandable language that you are going to use to express a query. Okay, so it can be understood by, a query language can be understood by the collection of functions or queries that you are able to express in that language. Later on, when we talk about how powerful a query language is, right, we are actually talking about how large that collection of functions or queries that you can express in that query language. So the first language we are going to talk about is called Relational Algebra. And that's actually very simple. So we are going to deal with this very simple database instance with 3 different relations. You have product, you have customer, and customer purchase product. Okay? So the high-level idea is in relational algebra is you can represent your query in an imperative way, because relation instances, they are sets. They are sets of tuples, right? So there's nothing stop us from querying it, from manipulating it using set operations. I could have a query language contain some basic operation over set, for example, a union between 2 sets, right? So my relation instance, they are set of tuples, right? There's nothing stop me from taking the union of them, producing a new relation, right? So I can union them, I can compute the difference between 2 sets, and then can compute the difference between two relations. I can do selection, I can do projection, I can do cross product, I can do renaming. We are going to go through each of these one by one later, right? And we can even do join between 2 different relations. But the high-level idea is because relation instance, fundamentally, they are sets, then we could run a set operation over those relation instance to create a new relation, right? So now let's look at some operations you are able to do in relational algebra. So first is union, okay? So I have relation R1, I have relation R2. My query could be just R1 union R2, right? That could be something I can write. It's the same type of the query. It's like take as input 2 relation instance, R1, R2, output a new one, which is a union of the 2 relations, right? So then you actually create some information out of your data now. So we can formally define what union really means, right? If I have a query, look like R1 union R2, what do we mean by some tuple is the answer of this query? That's something we can formally define. So again, right now you might think, why do we even go through this, right? So it's a union of 2 relations, of course, contains all the tuple of, both relations, right? But let's still try to define what is the answer to a query, because later on, when the query language becomes more complex, you will start to appreciate this formal definition about it, okay? So what is the answer to a query? If I have a query R1 union R2, it means that if a tuple X is in the answer of this query, it implies either X is in R1 in the input, or X is in R2, okay? This is a formal semantic of this query, R1 union R2, okay? So in this example, right, so assume you have 2 different relations, product 1, product 2. If you take the union, right, your output will be a relation instance that looks like this, contains all the tuples in product 1 and product 2. So again, right, you cannot union any pair of relation instance, right? So you can only union them with the same schema, right? In the sense that they have the same number of attributes, they have the same name, right, of each of those attributes, and then you know how to take the union, right? And you can compute the difference between two different relations. So again, the query might look like this. You have R1, you have R2, you have R1 minus R2, right? Formally, you can define it. A tuple X is in the answer of this query if and only if X is in R1, but X is not in R2, right? Again, if you take this example, you have product 2, you have product 3, right? If you want to compute the difference, the first thing you need to check is whether you are able to take the difference between these two, okay? So essentially, they have the same schema, right? All of them have 3 different attributes. All of the attributes have the same name, same type. So you are able to take the difference. Then it's well-defined, right? So if you take the difference between these two relations, right, you get a new relation look like this. Again, yeah, it's not valid if the schema of two relations doesn't really match, right? For example, if you have relation that's product ID and name, you have another relation, product ID and title, you cannot union them, you cannot take the difference, right, because you don't really know what that even means, right? So another corner case is, if I give you two relations look like this, I write down the schema like this. I have relation R with the schema PID and name. I have relation S. The schema is name and PID. Is that okay to union them? They look different, right? First one put the PID first, second one put the name first. This is the case that you are able to do it. Why? Because in the schema, you have a set of attributes. There's no order between attributes in relational model. Just like there's no order between different tuples in the instance, there's no order of different attributes, okay? It's a set. So you are able to do the union, even if the schema is written like this. And you can do more. You can do intersections between two different relations, right? So here, right, so if you write R1 intersects R2, right, so pretty much what that you are trying to do is the thing on the right-hand side. You can describe intersection using relation difference. So again, it's a very simple exercise, right? So you have product 2, product 3, the intersection, right? You find the tuple that appears in both, right? And you can do selection, right? This starts to become a little bit interesting. So essentially, you could run operation that take a simple relation and output only those tuples that satisfy certain condition. So the way to write it is to have a special operator called sigma, and then you have a condition C, and then that's specify the query. So what do we mean by this? Essentially, if the tuple X is in the result of the selection query over R, it means that the X must appear in R. It must be like you select. You cannot create a new tuples out of nowhere, okay? X must be in the original relation. But that's not enough. I also want the condition C, which is a logical formula, take as input X, output false and true, or true, right? So, and to be true. I want this tuple X satisfy this condition C, and then I put that in the result. You can think about it as certain like filter operation over the relation, okay? So just look at one example. Assuming I want to do a selection operation over product 2 with the following condition, that is price larger than 125. If you run this query, right, so what would be the result look like? Yeah, you are going to go through every single example in product 2, and you are going to check whether the condition hold or not. If the condition hold, you put that in the result. Otherwise, you ignore it. Okay? So in this case, you are going to have something look like this, right? You go to the first tuple, the price is smaller than 125, so the condition is going to return false, so not going to have in the result. For the second tuple, it satisfies the condition, you put that there. Okay? This is selection. And then you can do different type of conditions. For example, you can have a different type of selection query to say, yeah, I want to select over product 2. My condition is my name equals to BlackBerry, for example, right? And then you are going to have the result look like this. So, and the condition can be a little bit more complex. It can be logical formula, right? You can say, yeah, so here's a new selection query. The condition is I want the name of that tuple to be BlackBerry. I want the price to be larger than 125. Then you get an empty set, right? Because there's no tuples in the input relation that satisfy this condition. Okay? So again, an instance of relation is a set. So empty set is a valid instance. Okay? A relation instance can be empty. And you can do projection. Okay? You can think about selection as I filter on the rows, right? Projection is like I filter the columns, attributes, right? So once you can do is you can have this projection operator specified by, for example, A1 to AN, right? And you project R. So they only keep a subset of the attributes. For example, you have a relation product 2, right? You have 3 different attributes here. You have PID, you have name and price. And you'll say, I don't want the price attributes, okay? I want to project this relation to a smaller relation with only 2 attributes, with PID and name. Once you do that, right, what you are going to have? You are going to have a smaller relation with only PID and name, okay? So those are the 2 attributes that you write in the projection operator. So another thing is relation is a set, okay? There's no ordering between different tuples, right? So this is actually a valid answer to this query. As you can see, right, in the input, right, so I put BlackBerry first, Android second, right? So if you write this one, right, on the right-hand side as the answer, it's fine, right? Tuple doesn't have order, just like column doesn't have order. It's a relational model, everything is a set. And you can do cross product between 2 different relations. So essentially, you don't often see this in practice, but as you are going to see, it's going to be very useful, at least from the theory perspective, to express what join really is. So you have 2 relations, R1 to R2. You can compute the cross product between these 2 relations. Now, what do you mean by this, right? If a tuple xy is in the result of this query, if and only if x is from R1, y is from R2. Okay, it's cross product. Okay, for every single tuple in R1, for every single tuple in R2, you produce a new tuple. Okay, so look at one example, right? So assuming you have a customer, you have purchase, right? So you do the cross product. What are you going to have? Oh, you are going to have a much bigger table, right? How many rows are you going to have? In the input, customer have 3 different rows, purchase have 2 rows. So in the output, you have 6 rows, right? For every single pair, you create a new tuple in the answer. And then how many columns are you going to have in the answer? Yeah, so it's going to be the sum, right, of number of columns right here. I mean, for customer, you have 3 columns, purchase have 3. In the output, right, you have 6 columns, right? And then as you can see, for every single tuple in purchase, for example, the orange one, right? And for every single, and it's corresponding to 3 different rows in the output, each one of them corresponding to 1 tuple in the customer relation. So as you can see, it's very easy for this output to be extremely big. You have an input relation with like 1,000 tuples each. Your output will be 1 million tuples, right? So that's why in practice, it's very rare someone will do this. But from a theoretical perspective, it's going to be very useful. Okay? So one thing that's actually interesting is assuming in the input, I have my primary key. My customer has primary key, customer number. My purchase has a primary key, which is product ID and customer ID. Okay? So what is the key of the output relation, right? When you have a cross product. So essentially, it's going to be the combination of the primary key from the input. Okay? So in this case, it's going to be the combination of the customer ID from R1 product ID from R2, customer ID from R2. The combination of this going to be the primary key of the output relation. It's not very hard to see when you just sit down and think about this type of cross-product type of structure between these two relations. It will become clear. Okay. Another operator that we have in relational algebra is called renaming. So this one might look a bit weird, but it's going to be pretty useful. So essentially, I have my relation with n different attributes. Each attributes have their own name. And essentially, I'm saying that I don't like those names. I want to change the name. Okay? So I change those names to B1 to Bn. This is this operator. It just changes the name and do nothing else. Okay? So just look at one example. Right? You have the purchase relation, right, with 3 different attributes, PID, CID, and store. Okay? I don't like those names. I'm going to write a renaming operator to rename them to A, B, and C. Okay? So what is the output? The output has the same content as the input, but simply have different names for different attributes. And that's it. It might look very weird, but going to be very clear why we need this. Okay? So this is another operator in relational algebra you are able to write, just changing the name. Okay. So now let's look at a very important operator called join. And this is probably, if I'm writing SQL queries later in the course, this will probably the most important operator that you will see in database. A natural join looks like this. I have 2 relations, R1 and R2. And R1 has 2 attributes, A and B. R2 have 2 attributes, B and C. B essentially means that they match in name. Okay? So the natural join between these 2 relations is as the following. I first do the cross product between these 2 relations, R1 and R2. Okay? For every single tuple in R1 and for every single tuple in R2, I produce a new tuple. And then I filter them. I only select those pairs that matches on attribute B. They have the same value on B. And then I project them to A, B, and C. Okay? So this is essentially the semantic of this. It looks very long, but it's not that hard. So one way to think about it is think about you have the customer, you have purchase. Okay? Customer relation contains all the customer information, customer ID, the name and city. Purchase relation contains product ID and customer ID. The natural join between these 2 relations is simply to implement the following thing. That is, I have a customer. I know this customer buys that thing, right? I want to put these 2 relations together, have a table that contains the information of the customer, but also the product that this customer purchased. So that's the goal. I want to put this information, these 2 relations together. And the way that I want to put them together is to make sure my customer ID matches. So that is actually what we are trying to do. So if you look at this, right, so how do we get that output? So what we are going to do, right, is you enumerate every single tuple in the customer table, and you try to find the corresponding tuple in the purchase table that have the same value on customer ID. Because customer ID is an attribute that's being shared in these 2 relations. Okay? So essentially what's going to happen is you take the first tuple of the customer with customer ID CID equals 0, and you try to find whether there's a tuple there in the purchase table with the customer ID equals to 0, 2. In this case, that's the orange one. Okay? Then you are going to have a new tuple to say, yeah, this is my customer, 0, John Zurich. And also, this person purchased product 0, which that you get from the purchase table. Okay? And then you go to the second tuple in the customer relation, right? In this case, yeah, so it matches with the blue tuple there, right? So then you can output a new one. You go to the third tuple, right? CAD equals to 2. Yeah, I cannot find any tuples in the purchase relation with CAD equals to 2, so I generate nothing. This person buys nothing, right, in this universe. So this is natural join. So as you can see, it's going to be very important because this is the operator that allow you to put information together. Okay, make sense? So now let's look at something actually more complex, right? You can do multiple natural joins, right? You can say, yeah, I have customer, purchase, product. So customer table contains information on customer, product table contains information on the product, purchase table contains the connection between product and customer. You can do this two natural join, right? The first natural join is going to give you that table, right? So that's clear, right? It's going to link customer information to the product ID, right? And then you join that thing with a product table, you are going to get something like this, right? It contains the first three columns are from the customer relation, right? And then the last two columns are from the product relation. And then what's in the middle is actually from the purchase relation. So that makes sense, right? And then this is actually the beauty of relational algebra because my output is a table. I can actually stack a whole bunch of those operations, right, together to have an expression instead of a single kind of operation. So there are multiple corner cases about natural join that's actually interesting. And by looking at them, we can actually have a better understanding about what we are trying to do. So assuming I have two relations, I have R and S. And R has three attributes with the name A, B, and C. My S have two attributes with the name D and E. As you can see, there's no shared attributes. Okay? And I do the natural join between this. What would I get? Well, the way to do this is always go back to the formal definition of natural join. Right? As you can see, if I do not share those attributes, my selection operator in the definition will always be true, right? Because I'm matching an empty set, right? So essentially, you are going to have a cross product between these two relations, okay? So another corner case that's interesting to think about is assuming I have two relations that they share the name of all the attributes, okay? I have R, ABC as attributes, I have S, ABC as attributes. If I do the natural join between these two things, what would I get? In this case, again, go back to the definition, okay? So here, the selection operator will try to match all the attributes because all the attributes are shared, right? So I try to match all the attributes. The consequence of that is the only tuple that could be in the answer of this query, the natural join between those two relations sharing all the attributes, is those that would appear in the intersection, right? Only tuples appear in both have the chance to be returned, right? Because I'm going to take all the pairs of tuples, and the selection operator is going to match all the attributes, right? So I only output something when the same tuple appears in both relations, right? That's give you the intersection. So this is the two corner cases about natural join, right? So again, like go back to definition. It should be relatively simple to see why this is the case, okay? So any questions about natural join? This is a very important operator. I want to make sure everyone, we are on the same page about what it is. People here, people on Zoom? People on Zoom? No? Okay, great. So you can do more in join, right? So as you can see, the natural join gave you a really specific way for you to connect information. It is, yeah, I want all the value of the shared attributes to be the same, and then I put that two tuple together. You can have something that are more flexible than that. So you can have something called the Cita Join. Again, you join two relations together, but you have a condition to specify when do you output that pair of tuple. Okay? So essentially, if you have a Cita join between two relations, R1 and R2, what you are going to have is I do the cross product. I take all the pair of tuples from R1 and R2, and I only output those that satisfy my condition Cita. Okay? So this is Cita join. It's more flexible than natural join. You can actually implement natural in this way, right? So, and then you can do what we call equijoin, right? Which essentially, for R1 you have some attributes, R2 have some attributes, right? So I only return that pair of tuples when these two attributes take the same value, right? So this is something I could implement as a Cita join, right? So, and there are a whole bunch of joins that we are going to look at down the road, okay? So one thing that's interesting about relational algebra is that it has a pretty kind of modular kind of construction there. It's a single operator, the type, is something that takes as input a collection of relations and output a new relation, right? So that means I can stack a whole bunch of those operators together and form a bigger expression. So now let's look at this query. Now we are going to write our first query together. I have a database, customer purchase product, okay? My query is, I want to find out all the customers who bought iPhone, okay? So how can we write down this query as a relational algebra expression? So in this case, right, so this could be something that you can do. It looks very long, but if you read it, it's actually not that hard, okay? So how to answer that query is you look at in the middle, right? The first operation you are going to do is going to have a natural join between customer and the purchase, and then you do a natural join with product, okay? So that gives you a very long tuple. That is, this customer purchased that product with all the customer information, with all the product information, okay? That's what that two natural join try to do, try to connect those information. And then you do one selection over that big natural join, that is to say, I'm only interested in those customers who bought iPhone, right? I'm only interested in those big tuples that the name of the product equals to iPhone, okay? And then because in the query, you're only interested in the customers, you are not interested in all the other information, I will do one projection. I will project that very big tuple coming out of natural join and only keep the customer ID column. So this is one relational algebra expression that you can write to actually answer that query. So again, if you understand the semantic of every single relational algebra expression, like operator, right, the semantic of this expression is actually pretty easy to define. We are going to define the formal semantic of this in the next lecture. It's going to go to a little bit theoretical really fast, but intuitively it's very easy to understand what this thing is trying to do, right? So the way to think about it, right, is an expression. There's a recursive structure, right? You first do the natural join between customer and the purchase, and then you do the natural join between the result of that natural join with a new relation product. You do a projection over this. So the only reason you are able to do this is because the output of each intermediate operators is also a relation. That's the only reason you can actually stack them up. Okay? So there are some interesting operators in relational algebra that we can actually think about together. So let's look at this query. So I have two relations. I have one relation contains all the lectures. And then I have another relation, attends, which contains which student takes which lecture. Now the query I want to understand is I want to find students who is taking all the lectures. How can we write a relational algebra query for, like an expression for this query? So then we can go step by step, right? One thing we can do is, let's get the collection of all students, right? So I have a new relation called all students, defined by the following expression that I take the attendance table, I do a projection. I do a projection on the student ID attribute, then I get all the students, okay? Whatever answer you have to the query need to be a subset of all the students, right? You want me to give you all the students who take all the lectures. Let me find all the students and remove them who didn't take some lecture, right? So that is how we can approach this. We take all the students, and then we try to take those students who are missing some lectures, okay? How can we write that down? We can say, we take all the students, we cross-product with the lecture relation. That gives me all the pair of students and lectures in the first cross-product. And then compute the difference between all the possible pairs with the pair that you already have. This gives you which students are not taking which lecture, right? So this gives you that. And then if I do a projection on the missing lecture second step, I get all the students who have some lecture that they do not take, and they compute the difference between all students and students who have lecture that's missing, then you get the answer of this query. Make sense? Any question about this?
Does the projection automatically deduplicate the list?
Yes, it's a set. Yeah, so projection going to, Yes, okay. So projection going to automatically deduplicate because the output is a set. Yeah, you cannot have two elements that's the same in the set. Yeah. So essentially, I wouldn't think about that as operationally like deduplication. I would go back to the definition, right? So what is the answer of operator? Is I go through every single element in the domain. There's no duplication there, right? It's a set of domain. For each one of them, I check. There's no deduplication anywhere, right? But operationally, once you can do is you take all the tuples, take a subset of attributes, you deduplicate. And that's something that you are able to do, right? From the semantic perspective, from a theory perspective, there's no deduplication. From the practice perspective, if you want to understand this as a human, yes, there's a deduplication there, right? Any other questions about this query? Yeah, so this is actually the, I think, first non-trivial thing you'll see in the course, and they're going to be more like this in the next 3 months. So this is actually a very tedious thing to write. So luckily, there's a shorter version of this, which is something we call relational division. So essentially, there's a one operator that is attendance divided by lecture, right? And we have cross product, which multiplication. We also have the division, okay? So what we are writing here can be written down in a very simple form. That's attendance divided by lecture. Now let's talk about this relational division thing and try to think about why is this division, right? And how does that link to this query? So what is division, right? Yeah, division is the inverse of multiplication, right? That's almost by definition, right? And when we talk about relations, what is multiplication? Multiplication, we think about that as the cross product, okay? The division is actually the inverse of that. So what do we mean by this? So we have two relations, R and S. And our operator is R divided by S, get some answer T. So the answer T, the property that we want, is that the T is the largest relation such that if you compute the cross product between S and T, it is a subset of R. Okay? It's very different from computing the division between, for example, two real numbers, right? In that case, what is you have A divided by B, right? Give you C, right? What is C? C essentially a number that C multiplied by B equals to A, right? That's definition of division. For relations, little bit more complex because every single the thing I have there is a set, right? So you cannot have the cases that you can be evenly divided, right? So the best thing that we can do is we define the answer of the division as the largest relation such that, right, S cross product T is a subset of R. Okay? And you can define them like equally like in this more operational way, right? So what is the division between R and S, right? What you are going to do is pretty much you project R like onto all the attributes that is in R but not in S, okay? And then you just get rid of those, so like what you have on the right-hand side. It's very hard to read it out, but when you go back, when you think about it, that makes sense. You can actually prove if you define the division in the second way, it will satisfy the first definition, okay? So this is about division, okay? And then there are some other operators that we can write. So there's one operator that's interesting called semi-join. Okay, we talk about join, we talk about Cita join, we talk about natural join. There's something called semi-join, which has that very weird symbol. Okay, it's a half of join. Okay, and with a condition C. So the semi-join between two relations, you have R1, you have R2. Each one of them have different attributes, A1 to AN, B1 to BM, right? The semi-join between these two is the following. I do a Cita join between these two relations, R1 Cita join R2, and then I project to all the attributes of R1 only. Essentially, the Cita join, the semi-join between R1 and R2 are those tuples in R1 that I know going to appear in the result of the Cita join between these two relations. Okay, makes sense? I do the Cita join, and then I only keep those attributes that I have in R1. Okay, so that's all the tuples in R1 that matters for the Cita join. This is actually intuitively what you are trying to get by semi-join. So if you think about why do people have this thing, right? So why is this even useful, right? There are a lot of use cases of this, but let's talk about one of them. It's assuming, I said toward the very end of this course, we are going to talk about something like a distributed database. That is, I have a relation, you have a relation, right? And then we try to do join between our two tables that are not in the same place. And the question is, what information should I send to you such that we can do this distributed join together, right? Of course, as a system, I try to minimize the amount of information I send to you because otherwise it's going to be very slow, going to be very expensive. So that is where the semi-join comes in. There's a trick in distributed database called the semi-join reduction, which actually essentially try to do the following. That is, assuming there are two relations, R and S, right? They are on different sites. They are on different machines. One machine hold R, another machine hold S. So here is operationally how they can do the join. That is, I first do the semi-join of R with the projection of S on B, on the shared attributes. Okay? And then I join that thing with S. If you think about what it's trying to do, okay, is in the beginning, I have R, you have S. You send me all the unique value in your relation on B. I don't care about all the other attributes. I know we are going to join on attribute B. I want you to send all the unique value of B to me, And then I do a semi-join that I give you all the value in my relation that could be joined with your relation, and I only send that to you. Okay? This is actually try to minimize the communication in a distributed join. And that is actually one use case of this semi-join. It's called semi-join reduction in distributed database. So, yeah. So now let's look at some more examples. Now we define all those operators. We don't formally define, but naturally you know how to stack them together, right? So now let's try to write some queries. Let's go back to this database instance that we have been talking about today, about universities. Now let's say, yeah, let's get all the students who take database. How should we write that query? Right? So in this case, right, so we first define where should we get the information, right, to answer this query. Clearly, we need information of students of this relation. We need the information of the lecture. We also need the information of which student take which lecture, right? We are going to deal with these three different relations to answer this query. And one way to write it is, okay, let's join them all together, right? Students attend lectures, and then you have natural join between student and attends, which matches on student ID, and you do the natural join with lecture, and then you match the lecture ID. This gives you a huge tuple, right? Contains the student information, and then contains the lecture the student take. Okay, this is a really big tuple. So this is actually what you would have if you run the first natural join, right? Essentially what you're going to have is, look through every single tuple in the student relation, and you'll try to find those in the attends relation that matches student ID, right? In this case, you are going to have these two different rows, and then you do another natural join, you get something look like this, right? And then you can have a selection of those big tuple, only keeping those tuples that the title of the lecture equals to database. You have the selection there, and then you do a projection to keep all the students, and that's it. Okay? So essentially, this very long relational algebra, not very long actually, yeah. So this relatively short relational algebra expression is kind of one way to implement that query. It's not the only way. You can write other expressions, have the equivalent semantic to answer the same query, but this is one way for you to do that. And we can, okay, yeah, so that's all for today. So there's actually multiple of some examples, right? When you go back home, look at them. It's actually not that, not that hard to understand them, right? So in this course, we are going to write a whole bunch of them together. So don't worry, we cannot cover them today. That's it for today, right? So this is relational algebra. This actually gave you some ways for you to query the data. In the coming Wednesday, we are going to talk about another query language called Relational Calculus. And that's going to be very, very different from relational algebra. Yeah, that's it for today. See you guys next week.